Let's get started. Um, well, I guess we can just quickly recap what we've done last week. On Monday, I mean. We will go over homework 3 later. So basically, on Monday, we were talking about some concept of machine learning. So the first thing we talk about is like the concept of like in distribution and out of distribution. Um, So, the general goal of, deep learning and machine learning in general is to make the training distribution closer to the target distribution. And keep in mind that target distribution is always hard to define, is that you just try to define what your target distribution, think about what are the test case, where are you going to, use your models on, and what's the purpose, who will be using this. So think about all the different scenarios that potentially your models will be serving, who you are serving, what scenarios you want to have your model achieve. So once you define your target distribution, then you can think about how can you better make your training distribution closer to that. So we talk about overfitting and underfitting. So basically the concept is that, the automate function shouldn't be too complex, but it shouldn't be too simple. It should be somewhere in between so that it can generalize to, more data rather than, just overfit or, just customize too much on the particular data and the noise inside that data set. And then we talk about trend validation test split. So this is, the way that how we do it in machine learning. So the first thing we do is to just break your data set into, part of it is the training set, part of it is the test set. So test set, again, is an artificially created set that is just used to objectively evaluate your machine learning model. It doesn't necessarily actually capture the real test case that you're interested in using. Say, for example, we look at, does this animal classification model work on the, cartoon images, or does it work on painting of a cat or a dog? We don't know. I mean, because your test sets sort of define what you are aiming for. So anything beyond that would be out of distribution, and that's something very hard for the model that you train to be applied to that. So if our goal is to try to see if we can get the best performance on the test set, what we found is that if we just use this training set and put it on and use our model to do it, then we will easily get the overfitting issue. So the reason why we need the validation set is to have, a held out set, a portion of our data set that's held out there, so that we can sort of like try to mimic the test set performance. And so we evaluate our model on the validation set. So the general pipeline look like this. So we have a model and we just train it on our training data set. So we optimize it. So we get different version of it. So these different version of it could be, first epoch, second epoch, third epoch, or you try different learning rate, try different model, try various different things. But basically you get a bunch of different version of your model that is trained, but you don't know which one is better. And then you do the validation. So validation is selection rather than optimization. So you look at all these different training set, trend version of your model, and you pick the one that's working the best on the validation. And so the idea here is that if you train on this set where you have never seen the validation set, if the model can generalize to the validation set, then your assumption is that it should also generalize to your test set the best. So that's sort of the idea. Validation set is to see whether your model generalize out of the training distribution. And hopefully that will apply to your test distribution and also any other target distribution you're aiming for. questions on this? Like why? Oh, good. Cool. So without validation set, you will easily get something that's, overfitting on your training set. You, you know, it could work perfectly on your training set. Sometimes if you have a machine learning model, say a neural network, that's too powerful. Sometimes you can do, 100% accuracy, but it doesn't make much sense because maybe it's just looking at very weird details of your model. Try to remember each single image, like the details. Say, you see some background and then you recognize the background rather than the actual, cat or dogs images. So this is a typical, hopefully, or ideal training dynamics of your model. So when you train the model, the training loss will just go down. So it's obvious because we are using gradient descent. So at every step, even though there are some randomness inside it, generally the training loss will just keep going down. But that's not the case for validation set. As we said, there will be an overfitting issue happen at some point. So at some point, the model will get better on the training set, but it will do worse on the validation set. And that's where overfitting happen. That your model is trying to sort of like capture some unimportant details of your training set rather than something that can generalize to anything you've never seen before. So this is where on overfitting happened. And what we want is the model that has the lowest validation loss, which means that that model is the best we can do before the model is, overfit on your data set. Cool. So this we haven't looked at it. So let's continue our previous slide deck. Let me find it. Cool. So there's actually some way to overcome overfitting. It's not guaranteed you will fix it. To be honest, there's no way you can fix overfitting. But there are some way to hopefully make it less problematic. So early stopping is one of the way that traditionally people use to sort of like, it's not actually solving or preventing overfitting, but it's just a way to save some time. So early stopping basically means that after this after this stage, it's sort of like doesn't make any sense to keep training. So, we could just stop early. So that's basically the idea of early stopping is that, once you sort of know you've achieved the lowest validation loss, then you just stop early. So the trick here is to sort of like keep track of your minimum validation loss. And then usually we will set a tolerance that we will just keep training for a while and then just check if it's, never be lower, then we just stop it. So the idea is simple. Check if we are the lowest and wait for a while. And if it doesn't improve, then we just stop it. So this used to be the traditional way of, training machine learning model, but nowadays people actually found that sometimes it could be problematic because sometimes nowadays there are these kind of weird loss function. People are still trying to see why it happens, but sometimes it happens. So be aware of this issue. So either you use a larger tolerance so that you wait longer, or just don't use early stopping at all. So it could happen in this way that nowadays we have more advanced optimizer, we have more advanced training algorithms. They sometimes does not behave the traditional way. The other one that will be used in our homework 3 is dropout. So dropout is a very simple concept, but it turns out it's very helpful for preventing overfitting. So dropout, so that's it. each neuron may be removed with probability P during training. That's it. So that's the simple idea of dropout. So what does it mean? So, during your training, there could be a chance that some of the neuron will be missing. So these neuron will be sort of like turned off. It will be zero. So usually, you won't be applying on the output layer because output layer is where you get your output. It doesn't make sense that if you turn this off and this is the monitors. So in the middle layer and even in the input layer, you could turn something off. So think about something like in the input layer, it's sort of like you have a cat image and you just block part of the image, just make it all, zeros. So say you have a cat images, some cat image, and then you just block part of the image out. And hopefully, maybe you block the face of the cat. Then your model will start to learn to classify cats using the other body parts rather than, just relying on the face. But on the other hand, it could, block the ears, then the model has to leverage other features of cats and dogs to classify your images. So that's sort of the idea. So basically you just at each training round, you sort of have like different version of your model that part of it is it's gone. So that's basically the idea. And this probability P is called dropout rate. And usually it's around 10%, 20%, even though the theoretical best performance will be happening at 50%. But the larger the dropout rate, the longer you have to train the model. So people usually just try 10 to 20%, that you will get good enough training speed, but at the same time, better performance. So this is a plot. Well, basically what you can see is that with dropout, you can get better error rate. That's it. And then finally, sometimes you will see regularization term, but in general, there are so many different forms, but there are like two things that you might want to come back to the slides or, at least get a sense what L1 and L2 regularization. Sometimes you see lasso and ridge regression, but basically they have the same idea, is that try to encourage smaller weights, the model, and that has the ability to prevent overfitting. Cool. Questions on dropout and regularization? Hopefully not. Oh yeah, sure. So dropout is used in training only, usually. So during tests, you just put them back. So the idea is that, say these are different features of your say the animal classification case, say, does it swing, does it fly, does it blah, blah, blah. So, if think about it like, during the training, you just make it harder. Say you cannot use this, easy factor to classify your animals. So that's only happened in training. So during test time, usually we will put everything back. So yeah, dropout is basically used everywhere nowadays when you train the model, but you won't actually see that happen in the test time. Yeah, they will be back. Yeah. But I would say I think dropout is everywhere. Most of the model that I've seen today, they use dropout, because if you do use dropout, you usually overfit real quick. Yep. And as you will see in homework 3, it's just one line of Python code. So that's the case. The idea is simple, but to implement it seems a bit complex. But anyway, there are some some one-line code that you can do. Cool. So today, I think the biggest challenge we want to go through is to introduce you to convolutional neural networks. So this will be the core of homework 3. And, hopefully after my explanation, you could get a sense what CNN is doing. There's a lot of math, but I try to do it without much of the math. But hopefully you get the sense of what CNN is doing. Cool. So CNNs, the high level intuition is to learn reusable local pattern detector. So what does that mean? This is widely used in computer vision. You look at images, you see circles, you see, faces, you see different features that just happen again and again. Think about human face. We as a human has a very, very strong, human face detecting algorithm. Whenever you see something that looks like a face, you will just recognize it real quick. So that's sort of the idea of convolutional neural network, that we should just learn these pattern detector rather than some pixel by pixel deep neural network to learn about those. So it's widely used in computer vision, but it also widely used in music and audio, especially when you're representing music, symbolic music, sheet music as piano rolls. So like the one you see in, your DAW, GarageBand, or Logic Pro, when you click the MIDI file, you see that, piano roll. But also, we've done spectrogram in homework 2. So it looked like something like images, and there are, repetitive patterns inside it. So that's the way how we use CNNs in piano rolls and spectrograms. Cool. So what does reusable pattern detectors means? So basically what we want to do is that look at this image, there are 3 penguins. We can see that. But, for the model, it's just a bunch of pixels. It doesn't make much sense for the, for this model to sort of like learn to realize that there are 3 things, 3 equal or similar stuff going on in this image. So the idea of CNN is sort of try to see if we can somehow learn that pattern detector of a penguin, and then we can sort of use it to detect the other penguins. And this doesn't happen just within a sample, doesn't has to happen in this image only. Hopefully we can also use this learned pattern detector to sort of like detect other penguins in other images, and sort of like this image. But CNN, one thing we should also clarify is that we are not only learning those, very high level patterns that, the whole penguin that will be helpful for, animal detection, but we also want it to be hierarchically built up. What are the components of a penguin? How can we sort of like classify or, recognize that it is a penguin? So for example, we have beaks. So you can also reuse the beak detector if we can figure out what it means. Then in this case, it doesn't just use to detect, penguin, but it could also be used to detect, eagles or other birds. So that's sort of the idea. You learn different patterns. Some of them are very high level, just the whole penguin, but, sometimes it could be, smaller details, the beaks or the wings, the furs, whatever, the face, maybe. But the idea is that we want to learn different levels of patterns, and we want to reuse it across different images and within an image. So, think about when we are training like an image classification model, we have a bunch of different images. And what we want these CNN model to learn is to look at these images. What are something that's just happened across the data set? There will be different patterns just happening around, windows happen in other places, dog here and here, keyboards, flowers. They have different scales. They have different, shape and position within an image, but they sort of like share that same, shape or color-ish thing. So that's sort of the idea of CNNs, that we want to learn these patterns that can be reusable within an image and also across the image so that the model can do it more efficiently. Cool. So that's the goal. But in real life, it doesn't look like that at all. So this is the CNN architectural. So just a warning that this is something you will get in homework 3. So this is our goal. And this is our implementation, or the way how we do it to build a CNN models. We will talk about what CNN layers are, what pooling layers are, but basically you will just repeat this, convolutional layer, pooling layer again and again. And at the end, you will get something, deeper and deeper. So at the beginning, you will get something like a convolutional neural network. You will get something like this. And then you will do the pooling layer to sort of like reduce the resolution of it. And then you do more convolution layer. And then you sort of like aggregate more high-level ideas of your model. And at the end, you use those features to use the traditional deep neural networks to just put it over a bunch of fully connected layer to get your output. Well, we'll go over what these stuff mean in the next few slides. Cool. So what is convolution basically? So what is being done in these convolutional layer? The idea is not too tricky. It's just thinking about it like a pattern detector or pattern matching algorithm. So, this is 2D convolution. So we call, whatever input we have. So think about this as, some images, but in a weird shape, it's usually 0, 1, but think about it, maybe it's like 1 and -1. So this will be, darker pixels and, lighter pixels. And now we have something that we call kernel or filter. That's the thing that we want to learn. But for here, pretending that we somehow already figured out that we have this filter. So now what convolutional is doing, or within the convolutional layer, what we are trying to do is to just map this onto our input. So we first just apply this filter, this kernel, on the top left part of it. So you can just do element by element multiplication. So 1 times 1 minus 1 times -1 minus 1 times -1, and you go over it, and you will realize everything. It's a 1. Because negative part match the negative part, positive part match the positive part, and this is a perfect match because it's exactly the same. So when you have a perfect match, you will get something like 9. And that's the theoretical maximum value you can get from 1 to -1. So once you've done this, this is like exact perfect match. So you get a 9 in your output. Now let's move on to the next part. So now we slice it a bit at the right. So we look at the top right part. Now we apply this scheme again. You just times it. So now -1 times 1 is -1. Now, but we have -1, -1. So it's a match. It's a match. It's not a match, not a match. Sometimes it's a match. Sometimes it's not a match. So the red one would be a match, and the black one is not a match. So now you do the same thing. You just do the element-wise multiplication, and then you sum it up, and you get something like -1. So that generally means that it's not too bad, but it's not generally a match. So you get something like -1. And you do the same at the bottom left. Again, you can get -1 here. And now for the top, bottom right one, you do this again. Now it's a perfect match again. Everything just match. When it's 1, you get a 1. When it's -1, you get a -1. So perfectly, you will get 9 out of your 2D convolution. So, in the end, what you will get for the output will be 9 minus 1 minus 1, 9. So what does these numbers means? Basically, now you apply a filter based on the kernel that you have onto the input that you have. So you see a 9 basically means that you see this pattern at the top left part, and you see that pattern at the bottom right part. You didn't see that pattern in the top right part and the bottom left part. So, this is the idea of convolution. You are just sliding some filter over it and try to detect whether you've seen this pattern before. And whenever it sees the pattern, you will get something that very, in positive and something that's larger in its amplitude. Well, I do have some animation. So, look at these two knives. You actually get two perfect detection of your filter. For the 2-1, is where you don't have that pattern. So, you've sort of got this pattern detector in this case. Questions? Cool. Let's look at some negative example. Hopefully, you will better see why this is a cool idea to detect patterns. Now, if we look at this image, now there's no match at all. This is like some, this, how do I say it? This kind of pattern, but in our input is the opposite way, and there's no auto match. So if you look at the output, it's like 1115, basically means that generally we don't see a match in our in our input. But now if your kernel, your filter is different, now if your filter is in the correct direction, then now if you apply this to your input, you will see a 9 at the top left. So it will be 9 minus 1 minus 1, 1. So basically, that's what convolutional layer is doing, is that what we want to learn is the thing in the middle. That's the kernels. We want to learn a bunch of different pattern detector so that it can be applied to the image that you have, or the spectrograms that you have, the piano roll that you have. You want to say learn a C scale or C major filter, or you want to learn, I don't know, like a 4/4 filter, a D major filter, and then you want to apply it through your model to sort of do chord recognition, or you want to do tempo estimation. So that's the idea, and that's what convolutional layer is doing. So a convolutional layer consists of many learnable kernels. And we code it channels when you do it in PyTorch or TensorFlow. But basically, each convolutional layer, it's a bunch of different filters that is to be learned. So these are not free. You look at your image, you have no idea what are the filter that's most important to classify your inputs. So the model has to learn through the training that what are the important filters to detect the patterns that we need to classify our input images. So, think about it like this, you have different filters. Some of it will be, boundary detector, edge detector. Some of it will be color detector. Some of it will be, different thing. And, your output will maybe look like something like this. If it's an edge detector, if it's, I don't know, ice detector or blue detector, then everything will be sort of like grayish in the background and there's no activation in the front. But, you just apply different filter on it. And those filter is to be learned by the model. So each kernel sort of learns a local pattern. Questions? Good. So, that's sort of like what CNN is doing in the first layer. So the idea of CNN is to do this again and again and again and again, so that you sort of like compose more complex filters over time. We will see some example later. But basically, this is again what the CNN model look like. Some convolutional layer, pooling layer, convolutional pooling layer, and that's exactly what CNN models are doing. There are some details about convolution that you might see in homework 3, but we can just go over it. Well, actually, let me change the order of my slide. Let's go to where they should be. Well, actually not. I have to go through this. So one thing about convolutional layer is that you will see in our example that it actually shrink the model, shrink the input size. So if it's like a 4x4 image, or think about it like a pixel, this is like 4x4 image. Doesn't make any sense, but if it's a 4x4 with filtered by a 3x3 filter, you will get something 2x2. So usually that's not easy to deal with. So think about if you have a 32x32 image, after that it will become 30x30, and 30x30, if you just half it, it will be 15x15, and you will get into some weird numbers that's very hard to deal with. So usually in practice, what we will do is to do padding. So we will pad a bunch of like zero around the original images. So once you do this convolution, it will get the same shape. But it still do pretty good in detecting the positions of the patterns. So you still see a pattern here, but there's no pattern at the corner. Lower activation doesn't mean that there's no patterns. So padding is the way we do it. So in homework 3, you will see we are using padding equals same, so that you keep the original shape. So if your input is like 4x4, the output will be 4x4. It's much easier to deal with the shape. If you're doing padding equal valid, this is usually the default one. You will shrink your image, and sometimes it's very hard to deal with. In terms of how it works, your shape will be n minus k plus 1. So, and if you are doing padding equals same, you'll get the same shape. That's the sort of the shape that you will get. But generally, what you need to know is that, if you're doing padding equal valid, you will shrink your image. And if you are doing padding equals same, you won't shrink it. So sometimes it's helpful. There's another interesting about convolutional layer. We won't be using this, but it will be used in WaveNet, which is the CNN, convolutional neural network for waveform. So when you are dealing with waveform, it's like very high sampling rate. It's like 54.1K hertz, or even beyond that. So at that point, sometimes it's more efficient to jump across using our neural network. So that's what strike means. So strike meaning that we are not just moving this filter one at a time, one pixel at a time, to the right and to the bottom. So strike 2 means that you jump 2 pixels at one time. So, applying this strike equal to, you will get these 4 output only, because, that's you're jumping. And if it's strike 3, then you are jumping 3 pixels at a time. So sometimes it could be, more parameter efficient, but, you sort of also lose the detail information between the boundaries between these filters. So that's strike means, basically. And we also have this max pooling layer, which is in between the convolutional layers. So you see these stuff. So in this figure, you have a bunch of like convolutional layers, and you have this pooling layer. So pooling layer is where we sort of like downsample our images, so that you aggregate more high level understanding. So think about when you are doing animal classification. Look at a cat image, and, input is cat image. It could be, 32 by 32, 64 by 64, or even, 1024 by 1024 high resolution image. And your output is just that, cat or dog. So at some point, you have to aggregate that amount of information, 1024 by 1024, over the time into, more efficient, compact, understanding of, high level features. So that's why we need max pooling layers. Where's my max pooling layers? So max pooling layers basically just grab, say the top 4 things here, and we just look at the maximum, activation and put it here. And you do the same for the other stuff. So the equivalent effect of using max pooling layer is to, it's more like the classification case that, if you see, say, for penguin classification, you see a beak here, then you just only need to know, well, there's a beak at the top left-ish. I don't care where it is, but I do see a beak. So that's sort of the idea. You get rid of some of the detail localization or position information, but you just make it aggregated into a high-level representation where we sort of know where, sort of get a general sense where it is, and we do see that feature happen. So max pooling is a way to sort of like reduce the resolution over time, but aggregate those important features deep into the neural network. So generally, this is again the architecture that we are looking at. In the beginning, we have like RGB, it's 3 channels. So, or, you have grayscale image, then you have 1 channel of image. And over the time, the channels, so the patterns that we learn will increase as we go deeper. So think about this way, is that, originally you just need to sort of like learn some, filter that detect the edges, detect the, the colors. But after, when we go deeper and deeper, now we are looking at more complex shapes. So look at circle, look at triangle, look at corners, look at different angles of, boulders, or look at curve, and even higher level, look at, human face, look at, wheel, look at, I don't know, audio interface consoles. So, look at different stuff. So the deeper you are into the model, you are learning more complex things, and there should be more, pattern detectors in general, because now you are aiming for more complex stuff. Cool. Well, I guess we can go over the toy example to give you a sense, and hopefully, we just do it a different way, and hopefully you could get a better sense what's going on. So, this is a sort of like a toy example, and you will see something similar in homework 3. So this is like when you do this nn.conv 2D in channels 1, out channels 4, kernel side 3, padding same. So what does that even mean? So in channels 1, meaning that, input is like an image that's just 1 channel, and we want to output 4 different channels. And kernel size means that, your filter will be 3 by 3. So if it's just a number, if it's a 3, then it's, 3 by 3. You can also specify, a non-square filter. It could be 3 by 5, 6 by 7, or whatever that is. And padding equals same, so that, now we are doing outside of the box. We add additional padding outside of it so that our output will be the same shape. But basically what convolutional layer is doing is that you just grab this filter and just scan through your image and try to see whether you see that pattern. So, imagine this filter is sort of like doing the slope. Then you would just scan through the image to see whether there's a slope there. And you basically just do this over the whole, the whole image, and try to aggregate the output of that, pattern detector over time. And you are basically doing sort of like a scanning machine over your image and try to get whether you get the detection at different position. So now, we have like in channels 1, out channels 4, basically means that we are learning 4 different filters or pattern detectors. So here we have the orange detector, maybe is detecting certain feature, but now we could also have the green, pattern detector that's detecting a different, pattern. But anyway, we try to use our, deep learning model to learn about what this pattern is. But generally, what it would do when you apply it during test time is that it will scan through your model. And, you have different patterns, red one or, purple one. So basically, you will get like 4 different filters and you will get the detection output. So think about these patterns as, different feature extractors, say, detecting whether there's a beak, whether there's wing, whether there's fur, whether there's eyes in the background, whether there's, I don't know, penguin detector in the last layer. But generally, that's what we want to do. And what does the pooling layer do? Is that you will look at each different chunk of your detection, and now you get rid of like the detailed position information. You just care about whether we see something at that rough region. At the top left, do we sort of see that beak or do we detect a fur? We don't really care, the details about where it actually happened. We just only care whether we see that. So that's sort of like the max pooling layer is doing, for each single, block, you will just get the top, activation and you just store that. Cool. So in terms of implementation, it's nn.max pool 2D kernel size 2 stride 2. So kernel size meaning that you have a 2x2 stuff, and stride 2s mean that you're jumping. So usually this is the most common one. This basically just effectively downsample your input into a smaller version of it, and which is half the size. So this is the most commonly used, this is cat, most commonly used pair of convolutional layer. So you do a 3x3 convolutional layer with padding equals same. So you will keep the same shape. And then you apply the max pooling 2, then you get half the size of your input. So, you can think about this, doing it again and again. That's what we will be doing in homework 3. Then you just effectively make it, lower half the resolution until you get something you like. Cool. Well, there's a ironic animation error, but anyway, what we will be doing is just apply the thing you just saw. You do nn.conv 2D, you do this 3x3 convolutional layer, and you do max pooling, then you get a smaller version of it, but with more detection. So you have like 4 different features detector. It could be, think about slopes, boundaries, colors detector, and then you apply it again. Now you are, aggregating those shapes into, maybe circle detector, triangle detector, blah, blah, blah. But, you applied it again. And once you are done with, this convolutional layer, you basically just flatten it into one single long vector. So, look at this thing. There are 4x4, but 8 different channels. So you will just flatten it into 4x4x8, which is 128. So, at some point you will flatten it and then you will just do this classification. So the last layer would be the one that we just saw. You are using that, traditional neural network that you are just connecting those, learning about the weight, whether the first one is important, the second one is important, or the last one is important. And you just do weighted sum to see whether the output is a cat. And since we are doing flatten, basically what that means is that you are looking at the pattern detector output at the previous layer. So we basically use the whole information that we get here to classify whether it's a cat. So in real life, it will be some cat image. And then you just apply your model. You detect different features, and you will get different feature maps in the middle layer. And in the end, what you want to see if it is a cat. But it could be more complex depending on what your output is. So for homework 3, we are doing musical note classification. We want to see what the instrument is. So the output wouldn't be just like it's cat. It could be multiple things at the same time. Say here we are doing 3-class animal classification. Then it could be cat, dog, or bear. And of course, in this toy example, we are actually doing 16 by 16 pixels. So say goodbye to our cute cat. It would be something like this. But anyway, so in our homework 3, we are doing 64 by 64 spectrograms, which is already very pathetic. It's like, it doesn't look like the typical spectrogram that we have, but you will have to select a resolution in any sense. And the higher the resolution, meaning that your model has to learn harder on knowing what these pixels means. Because now effectively you have more pixels to look at, and these pixels doesn't generally have, you have to learn all these pattern detector from your model. We can look at this later. Well, can look at it now, I guess. So this is something that you might be using in homework 3. It's a little bit different, but basically this is how you define a model in PyTorch. So basically, you will get a bunch of like convolutional layers. So, input channel 1, and you want to learn 16 output channels on those inputs. And you are using a kernel size of 3. So 3 by 3 filters, there are 16 filters, basically. So imagine your input will be 64 by 64. So this is the case we were dealing with in our homework. So, it's a spectrogram. I've already processed it into, 64 by 64 images. So basically we can pretend it's something like images, even though it's not, but that's sort of the idea. And CNN doesn't actually have any assumption whether it's an image or it's a spectrogram. It just learns something. And over the time, it will become something like this. So 64 by 64 after the first convolutional layer, and then you apply ReLU, and then you apply the pooling layer. So effectively, it will become something like 16 channels, 16 channels of feature maps of shape 32 by 32. So you learn something about the image. You learn, different pattern recognition output, but in a lower resolution. And then you go over it again and again. So basically, over the time, deeper into the model, you get more channels, but lower resolution as we go deeper. And well, these are details, but that's the total number of weight that we are actually using in our model. And that actually decrease as we go deeper. Questions on this? Cool. Well, hopefully in homework 3, you get to play with it. You don't necessarily have to play with it. You just shift enter and just do something. But you will be actually training something like this. And this actually represent a CNN model. That's it. How many parameters? We could skip this. If you're interested, check the, you can actually compute how many parameters you have in each layer. Cool. So what's the benefits of CNNs? So just to sort of like have a conclusion is that, it learned local patterns rather than, some global thing, and try to learn local patterns. But over the time, when you aggregate the information, go deeper into your neural network, it will sort of like learn, higher level and higher level of patterns. And it's invariant to shift. So this is the technical way of knowing, understanding it. It's called translational invariance. But basically, that means your filter, what you learn, can just scan through your models, scan through your image, and it doesn't have anything to do with position. If you learned, cat face detector, you can apply it to the whole image, just scan through it and figure out where you see that cat faces. So it can also be applied to, an image with multiple cats, or, think about how we do, human face recognition. We as a human has super strong human face detector. And, that's sort of like invariant to shifts, whatever your head position is, wherever the person is, you sort of like get that detection correctly. So the idea of CNN is that we are actually reusing the learned filters across different parts of the image and across different images. And finally, that's important because it actually achieves higher parameter efficiencies against fully connected neural network. Cool. I think the last part would be the most fun. So what does a CNN learn? So, this is what CNN learns. So this is the first layer. So in this specific AlexNet, it's one, famous CNN model, which is a bit old. But anyway, this is what it learns. So look at watch out. So look at the first layer, which is 11 by 11 kernels. It's a bit huge, but anyway, you can look at what the first layer is learning. So some of it will be, looking at whether there's some pink colors, purple color, but a lot of it will be, slope or stripe, basically detecting, and these will be sort of like intensity detector, different intensity level and, colors. And, in the second layer, it just become much more complex that, it's detecting something, but it's not quite clear what it's detecting. So if you look at the first layer, so these are some of the, filters that the model learns. So this will be, like an edge detector. This will be a color contrast detector. This will be a just green color detector. So if you look at, so this is what they've done in this paper. Basically, just look at the image part that has the maximum activation based on this filter. You have different filters, and these are the things that trigger this detectors. So if you look at it, at the top left, you have this boundary detector in that specific shape, slope. So you can actually detect something like this. So this could be helpful if you want to do, I don't know, like door, or, think about it's a robot. You want to see where is the boundary. Maybe you will fall off, or, you want to see where the, the desk is, the screen is, or the door is. So these would be important low-level features so that you can get a sense what a bigger part is. But there could be also just, plain color block detector. So this is the green color, and you can sort of like detect the green colors. Some of it, it's not so clear to see. This is sort of like color plus boundary detector. So you see that, there are some color difference, but also the boundaries. And this one is much harder to see. It's also like a boundary, but, the color doesn't generally match, because you could potentially have different kernels that, detecting other color contrasts. But basically, you will see a colored, a slope somewhere in the image. So now, if you go deeper into the layer 2, these features actually aggregate into something more complex. So, think about this. You have different slope. So what the machine learning model do is that, think about, say, we want to get this. You can think about what the model will do is that in the first layer, you learn about four different um, filter. Say it's the four different slope. This. So, you will scan through the first layer image and you will get some detection out from this. And so think about the second layer of how we get this. It's actually sort of like combining these filters. So think about how we get the circle detector is that you can potentially just combine this thing and combine it with a filter here that's going from this to this, and then you get another filter that's going from top to bottom, and then you get something like this. Anyway, you get a sense that you can combine a bunch of different filters. That's you will get something like this, and then this, and then this, and then this, and then this. So then you get this bigger filter to detect the circles. So the first layer, you will be looking at these easy, just like different slope. But in the second layer, you will aggregate these filters to compose a much more complex filters. So this is basically just a bunch of different factors combined together, as you can imagine. But the deeper you are into the convolutional layer, it will become something more complex. So think about this corner. It can also be done by just combining this and this, and zero elsewhere. So you can think about just with these four different vectors filters, you can sort of like get a bunch of different variation of that. And that's what the CNN is doing. So you look at this, circle detector, you will detect, strong activation on circles. And you also have this corner detector that detect the corners. Questions? On how we aggregate filters or compose filters over the layers? Cool. You can just go with it. I mean, the deeper into our model, the weirder it gets, and it's harder to explain what's going on. And people talk about deep neural network as black box, and that's where we are talking about black box. At some point, still you see some grid detector. Well, it could be helpful to detect, I don't know, honeycomb or certain maybe windows, things like that. And you have like human detectors. Somehow, human is the most frequently captured object. So at this level, at layer 3, other layers, other filters are looking at different parts, but somehow we have human appearing here. So that's the CNN model figuring out that human just appears so many times. So at this point, we should already be able to detect the human. And deeper into layer 4, you see a huge filter that actually just detect the dog face in different angle. And you have this spiral thing. It actually captured different spiral things. So I believe this is a bug. And you have the camera, and you have the AC unit. You have, what's this? I think it's a cathedral. But anyway, it's this sort of like the same filter, just that it's applied to different, higher level concept of what spiral means. And it could be helpful to detect different stuff. This is the last layer. It's not the last layer. I think even later in the layer. So now you see, this, not just even the grid, it's sort of like a specific filters. And you see that it's detecting numbers and, digits or signs in general. So the deeper you are into the CNN, you see something more abstract. It's hard to explain what it is, but it's helpful in detecting the stuff that we are interested in. Cool. And so if you look at the activation of a trend AlexNet, can you guess what this is? This is the first layer after edge detector edge stuff. Dog? Close enough. Yeah, cats. I don't have the original image, but I mean, at least from what I understand, if you combine all of them, I think they have figures somewhere that's showing that this is a cat. Somehow, believe it. So you see the ears, and anyway, there's a face, and you see the body. So that's sort of what's being seen inside this uh AlexNet. So you see this, look at these different figures. It's actually different boundaries. So this would be the right hand side. So depending on the lighting, you see the right hand side. And this one sort of you see the left hand side. It's wide at the in the left, and you see different angles of boundaries, and also you see different patterns. And this is sort of like intensity filter. You see that it's dark. There's a cat shape here, and sort of like gray outside. And you also see, oh, there's a cat. It's obvious here. But anyway, cool. But if you go into fifth convolutional layer, you will see that this is the activation. So which means that, you apply some filter and you get something here. So, now it becomes very localized that you see something here. So this is likely the cat face, detector that has a very strong activation in the middle. And these are different filters taking into account different parts of it. This will be the cat body detector, cat ear detector, cat face. This will be background detector. So the model will just learn to have different detectors and apply it on different region of the images. This is also an interesting experiment that, just look at the image. So what it does is that they apply this patch over the images and to see whether they get the prediction correct. So red means that you are getting it correctly, and blue means that you are getting it wrong. So when you use this patch over it, so if you didn't block the dog face, it will be classifying dog correctly. But once you block the dog face here, then you see a very bad prediction accuracy. So it sort of suggests that CNN does look at the dog face to detect whether it's a dog, and then look at the cogwheel. It will be sort of like important stuff here, so that when you block them, the model has no idea of how to classify this image, and it will get it wrong. So basically that's sort of like a way to see what CNN model is learning, but it does have the ability to sort of like localize the object of interest. Yep.
Like edges of objects or the segment of image, or is there different techniques for that?
You mean this? Yeah, it's the same thing, but as we talk about here, the first layer is edges and colors, and then second layer it becomes circles, and then corners, and then the third level, the deeper you are into the model, you sort of like now you see wheel detector, different stuff, and you see higher level stuff. So this will be the whole thing. It detect edge at the first layer, but it also detect wheel at the last layer. And edge doesn't it's not close enough to whether it is a dog or a cat. So at the end, you still need to see whether this is a cat face or a dog face, or you want to see whether they have ears, how big they are. So you want other details rather than the edges. But edges would be the first thing that extracted by the model.
I guess I was more curious if it's like this is the way that you segment images.
Segment? Oh, I see your point. Nope. we usually train a different model to do that. But this could be the way. But it's less efficient. It's like you train the CNN for image classification, and then you do segmentation. But generally we train other models to do segmentation. Nowadays, for computer vision, they spend a lot of funding, so they actually get very high and segmentation. So they will have this image, And then we'll have another image that just has something like, something like this, the human here, and then the dog here, and then the human here. They will have like very accurately, this will be human one, human two, and then you will have, dog here, and then everything else. That's the kind of data they have, super high end, super expensive to get. So you have to have someone to actually fix, whether this is human body part or that's the background. So they actually have that kind of very high end, expensive training data to train their model. So this will be a very inefficient way to do it, but it does have some ability to do it. Cool. Questions? If not, I think we should just sort of try to get a sense what homework 3 is doing. So I assume you already have the account to Great Lake. Let me see. Can you try logging into it if you do have it? So the link, where's the link? So if you go to the instruction page, I assume you've already done this. If you haven't, just do this. And then you can log into your account on the web portal. So that's the link that I'm clicking here. Anyway, so once you're here in the Great Lakes, look at these, a bunch of stuff. But basically you will get some, 80 gigabytes of home directory. Anyway, what we would do is just look at this interactive apps, and then you click Jupyter Lab. And then, well, you can also choose it here. You can actually launch you can even do MATLAB, you can do different stuff, but usually we will just do Jupyter Lab. So you can choose different Python version. You can also do Mamba, but we would just be using the 3.11. Slurm account here I have two, but for you, I assume you only have this, but anyway, just choose the path 498 as blah 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 ish thing. And now partition is the tricky part. There's a bunch of different things. So usually we would either be using standard, which don't have GPU. If you do SP GPU, then you get the GPU. Number of hours depend on how long you need. If you set something too large, you might need to wait a couple days, couple of hours to wait until you get that amount of GPU available. But if you are requesting something less than, I don't know, 4 hours, 8 hours, usually you can get it right away within 5 minutes. Number of cores depends on what you need. But you can look at this thing, the instruction. So this is a recommended configuration of a GPU machine that's the most cost effective. So they have some certain limitation. If you do more, you have to pay more. So, if you request 1 GPU, you actually get 4 cores and 48 giga memory for free. If you want more cores, you can request more, but basically, this should be more than enough. So let's do SP GPU, and then number of hours, let's just do 1. I mean, we are almost ending the class. Number of cores, 4, and then we do 48 RAM. So once you've done that, number of GPU, just 1. You cannot request more than 1 for our account, but anyway. So you can click launch, and it will start. It will set queued, so that's when you are waiting the system to figure out where if there's any GPU machine available. Let's see how long we have to wait. Hopefully soon. Cool. But anyway, we can go over our homework 3 real quick. I do have HTML version. Whoops. Did I? Homework. There's a typo. Let's see. Yeah, it's starting and running. So when it's green, that means that you have the Jupyter notebook. So you can, click on the link to download the homework. Anyway, it's here. So, well, you can just download the Jupyter notebook and upload to Glade Lakes, or the other way is, just open it up in Colab directly. You can use Colab, but you can also use Great Lakes. It's up to you. For this homework, you do need to train it on GPU. So, Colab has, daily allowance. So if you fail to do this in one time, then you might have to wait until the next day. So on Great Lakes, it will be much easier. But you can still survive on Google Colab, likely. I mean, I've done pretty much 80% on Google Colab, and at the end, I was blocked, so I moved to Great Lakes. But you should be better. I'm doing a lot of back and forth developing. So once you've got this, you can see this as sometimes, if you launch something and you have to wait a bit and you go back to this page, you can click on this My Interactive Sections to see what are the sections. So these are the things that I was like creating yesterday to, develop the assignment. But now this is the one that we just launched. So we can click Connect to Jupyter Lab. Then you basically will get something that look like, not exactly the same, but basically something look like Google Colabs. So you can just upload your, homework, download the Jupyter notebook and upload it here. You can click this button to upload stuff. But anyway, I have the homework 3 here and also the solution here, but I won't click it. But basically, pretty much what you will be doing is, this will be the tricky part. You have to prepare the ANSYS data set. But once you've done with these part, follow exactly the, instruction to get these data set done. Otherwise, once you have the data set done, I've had data set here. Pretty much you just click Shift Enter over the time. Well, let's see. So now I am installing PyTorch, installing LibreOsa, and importing a bunch of JSON file. This might take a while the first time you run it, but I have already installed it. So now you can also see that we do have access to GPU. So this is the GPU that you get on Great Lakes. It's much better, NVIDIA F40, 48 gigabytes. We are sort of like wasting our GPU because our model is just, I think, less than 100 megabytes. But anyway, that's fun. What else? But basically you can just press Shift Enter all the time, blah, 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 blah. Once you've done with that, so what we will get is, there's no sound. Well, hopefully. Oh, that's the sort of the data we have. And, but we will be looking at a bunch of, mail spectrogram. So this is like 64 by 64 image. I've already processed it for you. So when you download the data set, you will just get a bunch of these images with their, class, guitar, acoustic. So basically what you want to train the model is look at this image, guess what the instrument it is. So, this is sort of like show our training set, the first 6 training data. So you have different spectrogram. And, even by looking at the spectrogram, you can sort of guess generally what those are. Base, it will be much lower end. And, organ is something that just keep all the time until 3 seconds, because the data set is that you press the key for 3 seconds and you lift it. So organ usually just look like this. So you can sort of get a sense that it's not a horrible task for the model to do. The model do have some queue. to guess what these are, but basically that's what we will be training the model. Well, pretty much that's what you will be doing. We will also create a data set in PyTorch, but for you, it's just Shift Enter. This step might take a while that it will have to go through the whole data set. So what this is doing is that it will just grab those data and then store it in the RAM. So temporarily memory on your on the machine that we have on Great Lakes, so that when during the training it worked much faster. So think about it this like, process it one time, and then in the future we will be fast enough. So, there are basically two ways of doing this is that, you can do it on the fly. Whenever you are training the model, you just grab something and then process it. Once it processed, then you start training. But here we are sort of like do the processing all at once at the beginning, and during training, we don't have to process it anymore. But basically you can go over it. So this will be the model. What we see, a bunch of convolutional layer. When you define it, it's like convolutional layer on the input image, ReLU, and pooling layer. And now we also have dropout. So this is like one layer. And the second layer will be the same. Apply convolutional again, nonlinearity, ReLU, do pooling layer, dropout. So you do it 3 times, then you get your model. And then you compile the model, and you have to move the device to move the model to the GPU. It should be, I try to make a bunch of commands, so it should be readable. So once you do that, you will see that we are actually using, well, not too bad. We are using 300 megabytes out of 48 gigabytes, which we are wasting the GPU. But anyway, that's our model, tiny model. That's only 35,000 parameters. But that's what it is. And you can just do the training. So we define cross entropy loss as our loss function. We use Adam as our optimizer. But you don't need to do anything on this. We use batch size 32 so that we can create a data loader on the data set that we have. And notice that we have to shuffle our training set. So whenever this, think about this training loader as, there are some data set. It's a mine that has a bunch of data set. So this training loader is sort of like a manager that's just like ordering a bunch of workers go to the mine to grab a bunch of training data and send it to the GPU that we want to train the model. And shuffle meaning that, every time you look at the data set, you have to do it differently. So this will be the biggest chunk of the code, but for you, just press Shift Enter and you will see. So over the time, what I did in this training loop is that after every epoch, that means that we go over the whole data set once, then it will, print, plot the current training and validation loss. So again, training loss is the thing at the behind, but it's never easy to see. So I do moving average thing. You will also see during training, it will show this progress so that you won't be, feel terrified without knowing what the model is going. So, epoch 1, epoch 2, you will see that validation loss will sort of stop at some point, and then training loss will keep going down. So, after the whole training, you will end up with something like this. This is when we apply dropout, that the validation loss will just stay here. If you don't apply dropout, usually the validation loss will just go up, as we see in the slides. So your task is just to run the whole script. You don't have to do any modification, just run it. And if you're interested in, look at some of the things, if you're interested in what training loss is, you can plot it. Or if you're interested in what this model is doing, you can print. If you're interested, the first question is asking what these are. So, you can calculate it, but you can also do something like print X shape at different layer so that you get the answer correctly. But that's what the first question is asking. So you can do it that way. But basically, other than that, you just do it. And what we need is this figure. you have to train it yourself. So you get a different figure than this. You get the training and validation curves. You also get this validation accuracy. And you also want to test the model on the test set. And you also want to apply it on a random waveform that it's clear, it's flute, but you have to apply your model to do it. So this is like the final layer that we get from the model. So, flute 0.85, but somehow it could be confusing with vocal string, but it will never confuse with other stuff. Maybe organ, but guitar, bass doesn't make much sense. So, hopefully this will make some sense for you. You can see the output of the model. But other than that, question one, you have to do some calculation, or you can also do the trick that I just said, print X dot shape to see what those are. But this will be question one. And question two, question three, just do everything else, don't modify anything. You should be able to get this figure, and that's what you need for question two and question three. Cool, we're running out of time. I would say the biggest challenge would be getting the data set. So follow the instruction and send me emails or post on Google Chat if you have any questions. If you face some issues, your classmates may probably face the same issue. So this will be something you want to do. Cool. So hopefully, or maybe, this will be the first deep learning model that you train. So have fun. I hope it's not the worst experience at all. You will realize that dataset pre-processing is the most time-consuming part, and I've done mostly everything for you. So your life is much easier in this case. Look at the pre-processing code. Homework 3. So I've done this pre-processing.html. This is what I've already done. So extract the male spectrogram. So basically extract like 64 by 64 images from the spectrogram from the waveform. So look at this. You have to run, I don't know, 30 minutes to get the processing done, and you have to write all the code, and you have to zip it. But basically what you get here, the zip files, these zip files. Oops, what have I just done? Anyway, they're gone, but I won't save it, but you will find it at the Google link. Cool. Questions? Or just book at office hour if you have questions. What is the partition and number of cores that we use? Go to the instruction page, and there's the recommended one. Just do that, this one. So partition SP GPU cores 448. This will be the default. Oh, and also note that the whole class has only access to a maximum of 5 GPUs. So it should be not the worst. Yeah. Well, yeah, but I mean, yeah, but generally we won't, it's the load, I would say, processing, you don't need GPUs. So when you are doing this processing, these stuff, do it with the standard CPU only machine. Once you are done, you just relaunch with a GPU so that you can run the rest. So do these part on CPU, or the other way is just do it in Google Colab, which would be, I don't know which one is easier. For Great Lakes, is that you have to do some stuff to get familiar with Great Lakes. It's not that like one-stop shop as Google Colab, but you don't need to wait as you will have to do Google Colabs. Cool. Sorry for going over time.